You think random means shapeless. Flip a coin 1,000 times, plot the results. Heads is up, tails is down. What do you get? A jagged line wandering up and down with no pattern. Random, chaotic, unpredictable. No structure whatsoever. That's what everyone believes. Random equals disorder. Random equals noise. Random equals the absence of pattern, the absence of shape, the absence of anything worth studying geometrically. Wrong. Random has shape. Random has structure. Random has a geometry so precise, so measurable, so universal that once you see it, you realize we've been blind to one of the most fundamental features of the natural world. Let me show you what I mean. Look at that coin flip path again, that jagged wandering line. Now zoom in on a small section. What do you see? More jaggedness, more wandering. The small section looks remarkably similar to the whole. Not identical, but similar in character, in roughness, in the way it wanders. Zoom in again. Same thing. The pattern of roughness persists. The line doesn't smooth out. It doesn't become predictable at smaller scales. It maintains its characteristic jaggedness no matter how closely you look. This is not supposed to happen. In classical mathematics, when you zoom in on a curve, it gets simpler. A circle magnified enough looks like a straight line. Any smooth curve examined at fine enough resolution becomes essentially flat. That's the foundation of calculus. That's how we've done mathematics for 3 centuries. Zoom in and complexity disappears. But random paths don't work that way. Zoom in and the complexity remains. The roughness persists. The shape of the randomness is preserved across scales. This persistence, this self-similarity of roughness is not an accident. It's a fundamental property of many random processes, and it can be measured, it can be quantified, it has a geometry. I spent decades studying this geometry, the geometry of roughness, the mathematics of irregular shapes, and what I discovered changed how we understand randomness itself. Here's the key insight. When people say something is random, they usually mean they don't understand it. They mean it has no pattern they can see. They mean it's unpredictable. But saying something is random is not an explanation. It's an admission of ignorance. It's a label we stick on things to make ourselves feel better about not understanding them. The real question is never, is this random? The real question is, what kind of random is this? Because randomness comes in different flavors, different species, different geometries. Think about it this way. There's the randomness of a fair coin flip. Heads or tails, 50-50, each flip independent of the last. Simple. Well-behaved, predictable in aggregate, even if unpredictable in detail. But there's also the randomness of a stock market crash, the randomness of a coastline's shape, the randomness of turbulent flow in a river, the randomness of how earthquakes distribute themselves in time and magnitude. These are not the same kind of random. They have different structures, different scaling properties, different geometries. The coin flip randomness is what statisticians call Gaussian. It's mild, it's tame. Extreme events are rare. Everything clusters around the average. If you flip a coin 1,000,000 times, you'll get close to 500,000 heads. The deviations from average are small, predictable, well-behaved. But market crashes aren't like that. Earthquakes aren't like that. They follow what I call wild randomness. Extreme events happen far more often than Gaussian statistics predict. The distribution has fat tails. Single events can dominate the entire history. These two kinds of randomness have completely different geometries. And you can see the difference in the shapes they produce. Let me make this concrete. Take a random walk. Start at 0. Flip a coin. Heads, move up 1 unit. Tails, move down 1 unit. Repeat. Plot your position over time. You get a jagged path wandering around 0. Now, measure the roughness of that path. How do you measure roughness? You look at how the path varies across different scales. How much does it move in 1 step, in 10 steps, in 100 steps, in 1,000? For a simple random walk, the variation grows with the square root of the number of steps. Take 100 steps and you've typically wandered about 10 units from where you started. Take 10,000 steps and you've wandered about 100 units. The square root relationship. This scaling law is the geometry of the randomness. It tells you something fundamental about the structure of the random process. It's not just noise. It's not just chaos. It has a measurable, predictable, geometric property. But here's where it gets interesting. Not all random processes scale the same way. Some are rougher, some are smoother. The exponent in the scaling law varies. For the simple random walk, the exponent is 1/2. But for other processes, it might be higher or lower. A process with exponent 3/4 is rougher than one with exponent 1/2. The path wanders more aggressively. The fluctuations are larger at every scale. This exponent is directly related to what I call fractal dimension. It measures how the roughness fills space, how the random path occupies the plane, how complicated the geometry really is. A straight line has dimension 1, a plane has dimension 2, but a random walk path is neither. It's somewhere in between. It has a fractional dimension, a fractal dimension that captures its essential roughness. For a simple random walk on a plane, the fractal dimension is 2. The path wanders so thoroughly that it eventually fills the entire plane. It visits every region, covers every area, given enough time. That's remarkable. A one-dimensional path with the covering properties of a two-dimensional surface. Other random processes have different fractal dimensions. Some fill space more efficiently, some less. The dimension tells you about the fundamental geometry of the randomness. This is what I mean when I say random has shape. The shape isn't a specific pattern, it's a statistical geometry, a way of being rough that persists across scales, a fingerprint of the underlying random process. Now, why does this matter? Why should anyone care about the geometry of roughness? Because the world is rough, not smooth. Rough. Look at a mountain range. The profile is jagged, peaks and valleys at every scale. Zoom in on a single mountain and you see smaller peaks and valleys. Zoom in further and you see rocks and boulders creating more jaggedness. The roughness persists down to the scale of individual stones, individual grains. Look at the coastline. The boundary between land and sea is not a smooth curve. It's infinitely intricate, bays within bays within bays, peninsulas with smaller peninsulas. The closer you look, the more detail you see. The coastline never smooths out. Look at the cloud. The boundary isn't a simple surface. It's a complex, turbulent, ever-changing shape with structure at every scale, wisps and tendrils and billows nested within each other. Look at a tree, the branching pattern, the texture of bark, the shape of leaves, roughness everywhere. Look at your own body, the convolutions of your brain, the branching of your blood vessels, the surface of your lungs, rough structures that serve biological functions precisely because they are rough. The world is not made of the smooth shapes that classical geometry studies. The world is made of rough shapes, and for centuries mathematics had no language to describe them. That's what fractal geometry provides. A language for roughness, a way to measure and classify and understand the irregular shapes that dominate the natural world. And here's the profound connection. Many of these rough shapes are produced by random processes. The coastline is shaped by random erosion and deposition over millions of years. The mountain range is sculpted by random geological forces. The cloud is formed by random turbulent mixing of air and water vapor. The geometry of these shapes and the geometry of the random processes that created them are the same geometry. The fractal dimension of a coastline reflects the scaling properties of the erosion process. The roughness of a mountain reflects the statistics of geological forces. Understanding random processes geometrically lets us understand the shapes they produce. And conversely, measuring the shapes tells us about the processes that created them. This is not just theoretical. It has practical applications everywhere. Consider financial markets. Stock prices wander up and down in what looks like random motion. For decades, economists modeled this as simple Gaussian randomness, mild fluctuations around the trend, well-behaved statistics, but that model fails catastrophically. Real markets have crashes, flash crashes, sudden moves that Gaussian statistics say should happen once in billions of years, but actually happen every few decades. Why? Because market randomness isn't Gaussian. It's wild, it has fat tails, it has a different geometry. When I studied cotton prices in the 1960s, I found scaling laws that didn't fit the standard models. The fluctuations at different time scales had a specific relationship, a geometric relationship. The roughness of the price path had a measurable structure. This structure told me that extreme events were far more likely than people assumed, that the same patterns appeared at daily, weekly, monthly, yearly scales, that the market had a fractal geometry. Understanding this geometry doesn't let you predict the market. You still can't know when the next crash will happen, but it lets you understand the risks. It lets you build models that don't catastrophically underestimate the probability of extreme events. It lets you prepare for the inevitable wild swings that smooth Gaussian models pretend don't exist. The same principles apply to natural disasters. Earthquakes follow power laws. The frequency of earthquakes of a given magnitude follows a scaling relationship. Small quakes are common. Large quakes are rare, but the relationship between frequency and magnitude has a specific geometric structure. This structure tells you about the underlying physics, about how stress accumulates and releases in the Earth's crust, about the fundamental randomness of fault systems. It doesn't let you predict specific earthquakes, but it lets you understand the statistics. It lets you estimate how often magnitude 8 events occur. It lets you plan and prepare based on the true geometry of seismic randomness rather than wishful thinking. Here's another way to think about this. Classical statistics assumes that extreme events are outliers, aberrations, things to be ignored or smoothed away. The focus is on averages, on typical behavior, on the bulk of the distribution. But for many real-world processes, the extremes matter most. The biggest earthquake causes most of the damage. The worst market crash wipes out the most wealth. The strongest storm does the most destruction. The geometry of roughness, the geometry of wild randomness, is precisely the geometry of extremes. It tells you how the biggest events relate to the smaller ones, how the tail of the distribution behaves, how to think about rare but catastrophic occurrences. Ignoring this geometry means ignoring the most important events. It means being perpetually surprised by the inevitable. It means building systems that fail precisely when they matter most. Now, I want to address something fundamental. When I say random has shape, I'm not saying random is predictable. I'm not saying we can forecast specific outcomes. Randomness remains random. You still can't predict the next coin flip, the next stock price movement, the next earthquake. What I'm saying is that randomness has statistical structure, geometric structure, structure that persists across scales and can be measured and classified and understood. This structure is as real as any physical property. The fractal dimension of a random process is as measurable as the mass of an object. The scaling exponent is as fundamental as any physical constant. And this structure matters. It determines the shapes that random processes create. It determines the statistics of extreme events. It determines how systems behave across different scales. Understanding this structure is not a substitute for prediction. It's something different. It's understanding the rules of the game even when you can't predict the next move. Let me give you an analogy. You can't predict exactly where a drop of ink will spread in water. The turbulent mixing is too chaotic, too sensitive to initial conditions. But you can understand the statistics of spreading, how the ink disperses over time, how the boundaries of the ink cloud develop their characteristic roughness, the geometry of the diffusion process. That understanding is valuable. It lets you model systems, design processes, make decisions under uncertainty. Not by predicting specifics, but by understanding the statistical geometry of what's possible. This is what I've tried to give the world. A geometry for the unpredictable, a mathematics of roughness, a way to see structure in what looks like chaos. The old view said smooth is normal and rough is deviation, rough is noise, rough is error, rough is what you get when things go wrong. I say the opposite. Rough is normal. Rough is the default state of nature. Smooth is the exception, the special case, the idealization that rarely occurs in the real world. When you look at a coastline and see infinite complexity, you're not seeing disorder. You're seeing a specific kind of order, a fractal order, an order that expresses itself through roughness rather than smoothness. When you look at market fluctuations and see wild swings, you're not seeing irrationality. You're seeing the natural geometry of complex systems with many interacting parts. Systems that produce wild randomness as naturally as rivers produce turbulence. When you look at clouds and mountains and trees and blood vessels and river networks and earthquake catalogs and turbulent flows, you're seeing the geometry of roughness expressing itself over and over in different domains. This geometry is universal. The same mathematical structures appear in completely unrelated systems because the underlying scaling laws, the underlying statistical properties have a geometry that transcends specific mechanisms. Understanding this geometry means understanding something deep about how nature works. Not the smooth, predictable, clockwork nature of classical physics, but the rough, irregular, scale-invariant nature of the real world. Classical mathematics gave us tools for smooth shapes, calculus, differential equations the geometry of curves and surfaces. Fractal geometry gives us tools for rough shapes. Scaling laws, power laws, the geometry of irregular boundaries and wild fluctuations. Both are needed. Both are valid, but for understanding the natural world, for understanding the shapes that actually occur, for understanding the randomness that actually operates, fractal geometry is often more appropriate. The next time someone says something is random, ask them what kind of random? What's the scaling law? What's the fractal dimension? What's the geometry of the roughness? Because random is not the absence of structure. Random is not the absence of shape. Random is not the absence of geometry. Random has shape. And that shape can be measured, classified, understood, and used. The world is rough. Mathematics should be too. Not comfort, not smoothness, truth,